Wonderful. So it's basically now being recorded on both.
Yeah.
Okay,
Yeah,
wonderful.
we'll start recording when this goes red.
Okay, got it. Wonderful.
So
Okay, thank you. And I'll join the teams here so that I can also
yeah,
see if there are any.
it's very good system.
Okay, yeah, so I just keep them separate because it mixes them all together. Yeah, it's like a separate, yeah, okay, so it's perfect. Now you can see, also see the chat here. Awesome. Okay, thank you so much. Oh, thank you so much. Thanks a lot. Thank you. Thank you. Okay, hello everyone. Good afternoon. I hope you've enjoyed the course so far. Today we're going to start a new section in the module, which is soft tissue. So we're going to look at all those organs that have soft compliant tissue and have functionality within the body. So far you've looked at teeth, but also generally the bone tissue. In terms of the course content, it may have been a little bit more challenging at the beginning, first 3 or 4 weeks. Now we're going to get it a little bit lightened up, but still we're going to continue the same flow. We're going to have 2 more lab sessions. Were you all able to attend the first one? Everything worked fine? Amazing. So we're going to have 2 more. The first one's going to be after week 7, in week 8. So week 7 is absolutely empty, not going to have any activities. I'm probably going to upload some papers for you to read for the upcoming weeks, so there's not going to be any asynchronous or synchronous lectures, maybe some asynchronous actually, which I will upload as well. I looked at the viewers for the video that I uploaded, and I think there were just about 25 of you who managed. I'm not sure if it's not displaying the correct number, but please make sure that you view the videos, the asynchronous content ahead of the in-person lectures, because if you don't, it's going to be difficult to make sense of the material that we cover here. I encourage you to come and attend the lectures in person, but if you can't, I'm still using the Teams link that we used before, so that you can actually join online. Okay, so one last note, the Padlet that Karen kindly set up is still going to be the same Padlet link for the next couple of weeks. So if you have any questions that you want to bring up regarding the asynchronous content, please just add it under week 5, 6, etc. In that same Padlet. Okay. Yeah, I think that's pretty much all in terms of the logistics. Today we're going to talk about, so we're going to complete what we started. Now you may be wondering, why do we have so much biofluid mechanics in this? Why do we have so much anatomy? It's critical that you understand this system, and this system, your heart, your cardiovascular system, is mainly a fluidic network. That's why the nature of it is basically a pump and some piping. That's why understanding the proper dynamics of this environment, the physics behind the flow, is going to be essential to your understanding of how the devices work in these systems and what the critical aspects are when you're choosing material. Okay? So what's going to happen in the next week's content, we're a little bit behind, so we're going to cover the diseases first, and then we're going to look at every specific disease. Why is it caused? Is it related to flow? And you'll see that the majority of them are. So the questions that you actually brought up, laminar flow, shear stress, those are the factors that actually influence your health in the cardiovascular system. So when we get to each of these individual diseases, it's going to make a lot more sense now that you know everything about the flow profile. We're going to look at the diseases, then we're going to look at the various devices, heart valve, stents, and you're going to understand the specific workings of these and why we've chosen certain materials to make these devices. And then in the next session in class, we'll be talking about innovations. We're going to get a little bit more creative and think about new solutions for that. Today, though, we're going to sort of try and complete your understanding of the biofluid dynamics, the fluid dynamics of our biological system. And for that, starting with this beautiful photo of a leaf, it's actually very interesting. The same principles that govern the formation of these vessels, the geometry of these vessels, are those same constraints that define the formation of your blood vessels. It's something that we call the Murray's law, and we'll get there in a minute. But I actually posed a set of questions in the third lecture, which are really crucial to your understanding of blood flow. There's not that many various contents that you have to be aware of. There's not that many concepts out there, but these three are really critical. You've got to know what the answers to these questions are. So the first one is, why do we even have fluid flow? Why do we have a bulk flow rather than diffusion, which is very cheap? It happens naturally, okay? If you put a droplet of ink in a glass of water, it's going to diffuse that water. Your body is made out of water. They could have just done that, right? Could have just allowed the nutrients to diffuse. Well, the situation is that diffusion is very slow. And when I say slow, you may feel like, okay, the droplet of ink actually diffuses very fast. Why is it that it takes so long for our bodies? I've actually put a numerical example there. So diffusion time has a proportionality with the length, how long of a distance you have to diffuse. You guys have seen this before in the materials engineering module. But the length of the path it has to diffuse and the diffusion coefficient. Now, for the diffusion coefficient of water, for instance, which is 10 to the negative 5, okay. So for the diffusion distance and the diffusivity of water within your body, let's bring a couple of examples. If you had a 1 millimeter distance and you wanted oxygen to diffuse through this distance, a molecule of oxygen, it would have taken 17 minutes. If you have a 10 millimeter distance, the thickness of your finger, diameter of your finger, it would be about 10 millimeters, right? And it would take about 1700 minutes to diffuse. How long is it going to take for a human body that's not actually 10 millimeters, but instead 1700 millimeters? Wow, it's going to be a lot more because it has a relationship that is square of the distance to diffuse. So it's going to be a crazy amount of time to diffuse oxygen from your head to your toes. Okay? So this is critical that you understand how terribly slow it is, right? Now, if it gets to the capillary levels, it's going to be easier. Because down there, you're in the proximity of 20 microns from every cell. That's how far. So it's interesting. Our arteries go to the arterioles and then the capillaries. And the capillaries, the farthest distance between two capillaries is about a third of your hair in thickness. It's about 30 microns. And that is amazing. That's why that's super fast to now diffuse. But we have to get it to that level first. That's the reason we have flow. And when it comes to flow, we have a simple model for flow in a tube. You've seen this in fluid mechanics. It's the Poiseuille's law. It's derived from the consideration of no-slip boundary condition and the Navier-Stokes equation, and basically assuming that parabolic flow profile. If you do all those derivations, you'll figure out that there's a relationship between the pressure difference of the two ends of the pipe and the flow rate. And that has to do with the geometrical features of the pipe and the viscosity. Because it's friction, because it's the viscous forces, the drag forces from the liquid rubbing against the walls and trying to make its way through. Now, with that, we actually like to look at it as a resistance model, right? So we have the voltage difference is equal to current times resistance. We have the same for fluids, right? We have the resistance, the fluidic resistance, times the flow rate gives you the pressure difference. So in that form, it's easier for us to make circuit models. So when we analyze the human body, we have a lump model. where we model the aorta with the resistance, the hearts with the capacitance, resistance, and an inductance. That's how people in the research area, before they start a FEM model, to look at it much more finer, they have to make a lump model of the entire circuit, and they put in the pressure for the heart, they get the pressure for down here in the leg, which is all an electrical circuit connected together. Okay, and this is why knowing the behavior of each of these circuit elements is going to be crucial to designing, let's say, a valve for your veins in the leg. Right, you need to know what pressure you have there for that valve that you're putting there. If it's a heart valve, similarly, you need to know the pressure differences. What's the maximum? What's the minimum? What are the working cycles? Okay, so it's crucial that you understand this very well. Now, the second question is why do we have a variety of sizes? And I've already answered that. That's because diffusion is very slow, right? So if we went from the heart all the way to the entire body with capillaries, it would have too much resistance, right? As I showed you, it has relationship with the fourth power of the radius, right? So it would just be crazy resistance. Your heart couldn't pump it through all those capillaries. So we have to start with the larger arteries and then get it to narrow down all the way to capillaries. That's how evolution has enabled the optimization of these systems. And it's there for leaves, it's there for molds, it's there for your human organs, it's everywhere in these natural systems. It's the same structure. So now, you had a couple of very good questions. One was that, why do we have this much blood in the veins? Why is it important to have that for our, we know how. There's one question, is how do we have that? Why does it happen? The other is, what's its importance and effect? We'll get to that. And what do we mean by a damping system in our veins? Okay, what does that damping system do? And there's the third question here about laminar flow. What happens if we have turbulent flow? What happens if we have... This we'll get to. This you will see in disease modeling, as we will get to, that the non-laminar flows, the turbulent flows, are what starts to initiate the plaque formation and trigger the thrombosis events and platelet coagulation. We'll get to that in the next lecture, but for now I'm just going to respond to these first two. Let's look at these two, veins versus arteries. What are the differences? From this image, what can you see? What's the difference that you can see between the vein on the right-hand side and the artery on the left? Yep, perfect. Thinner wall, perfect. The vein has a thinner wall, so it's more compliant. Any other? Yep. It has a bigger lumen, yes, exactly. The overall internal diameter and the average diameter is going to be larger than that if it had actually shown that correctly. What else can you see there? Yep. It has a valve there. Exactly. What are you going to say? Yep. Exactly. So there's a different structure of layers of that. Perfect. You've actually pointed out all the various differences. Now, this being thinner, the wall being thinner, larger medium diameter, or average diameter, causes it to have more compliance. When the blood comes in, it expands, right? Just the bellows, just like as a fluidic sort of sac, like a balloon when you blow air in it, right? It expands, right? The reason we call it a capacitor, and the reason we say that it has capacitive function, is because of this compliance. Now, I'm going to explain that in a moment, then we'll get to why we have a valve in it. So, we have three circuit elements in electronics. We've got the resistance, we've got the capacitance of the capacitors, we've got resistors, capacitors, and we've got inductors. And I've written them all as a function of current. So, a resistor, the voltage is proportional to current. And that proportionality factor is R, the resistance. When it comes to a capacitor, I don't know if you've looked at it like this before or not. A capacitor integrates the current that's coming into it, right? It's an integrator in the circuit. The relationship between the voltage and the current is an integral relationship, meaning that if you gradually increase your current, right, it's going to integrate and basically receive more and more electrical charge on the two plates, right? As you accumulate that through time. If you look at time zero, there's no voltage between the two plates, but as the current goes through, you're building up charge on one plate and the opposite on the other. Now the voltage is building up. I'm not going to get to the inductor just now, because it's going to be really difficult to show you a fluidic inductor. But for these first two, we're going to focus on those. Now, if you look at a regular pipe, we just showed that it has a resistive behavior. So that's the performance of a pipe. Now, what if we put a deformable membrane here, or if we make the pipe compliant so that it can expand and go back to its regular size? What happens here? I'm going to write the same equation, and this plot is hopefully going to help you understand what's going on. If I'm drawing this is supposed to be, so volume versus pressure. So if I draw the volume versus pressure curve for the first one, which is just the resistance, as I increase the pressure, what's the volume inside that vessel going to look like? It's going to remain constant because it's rigid. The walls are rigid, right? Okay. What if I actually have that deformable membrane? As I put more and more pressure on it, it will gradually increase the volume of the vessel, right? Now, at some point, this is going to plateau because this is no longer, it can't just expand forever. But it's going to slowly go, the slope is going to drop as it builds up. And if I continue on making the membrane less and less stiff, more and more flexible, this curve, well, right now I've approximated it with a line, it's going to actually have a great slope. Now, why do we look at the integral? Because the surface, the area underneath this is expanding, right? As I increase the slope. So as I increase the capacitive behavior, the compliance of this, the area, the integral is going to increase. And what that means is that the volume difference between the terminal point and the initial point when I injected the flow is going to be greater, right? And that's going to build up more and more pressure. So pressure build up in this isn't linear with the flow. As I increase the flow, at least to some level, it's going to increase the pressure there. Just the way your heart, when it expands, you have a curvature that it follows for pressure build up. It's the same for your veins. And that's what I'm trying to explain here. Any questions about this? Does this make sense? Awesome. So now let's look at the big picture. So what happens when you have a large capacitance there on the vein side? It's going to act as a couple of things. First of all, it's a reservoir. So it's interesting that the 60 or 70% of blood that stays in your veins acts as a reserve. When the heart cannot maintain flow, it actually uses that to circulate to the organs. So it's the reservoir there. The second thing, and here the valves are also important, the veins in your legs, in all your organs, they have valves in there. And what the valve does is it avoids or sort of prevents the flow of blood to go the other direction. It's just like a bicuspid valve, right? And flow can only go in one direction. All of this is to build up a reservoir here so that it assists the heart in producing that pressure. It doesn't put that backload on the flow here, right? So if you really look at the entirety of this circuit, we've got a distribution site at the artery level. We've got the resistance building up the capillaries, which slows the flow and allows it to basically distribute everywhere. We've got exchange right at the capillary levels, and then we've got the capacitance on the vein side, which actually fully dampens it. And also, you shouldn't underestimate this full dampening that happens here by this time. If this side, the vein, did not exist, this would have gone on although the capillaries are so tiny that the flow is definitely laminar, but there would have been an oscillatory element to the pressure levels, and that wouldn't have been good for the consistency of the tissue growth in the proximity of this the blood vessels. Okay, the tissue in our heart can handle that level of oscillation. It's designed to sync with that, right? That entire beating is what keeps those cardiomyocytes alive. But in the other organs, it's not the same story. If you give them that same oscillation, it's going to change their growth pattern. So that's why we have to have dampened it to a laminar and constant pressure flow by the time that it reaches the organ of interest at the capillary level. Okay? So, now to the third and last question. Any questions so far? Okay, so this is probably the trickiest to answer. And that is, if we look at these fluidic elements, as I mentioned, we go from the aorta to the arteries, to the arterioles, to the capillaries, and it's all reducing in size, which is great, right? Because it means that we have a shorter diffusion distance, we can now get really close to the tissue. But what it means is that now, if you reduce the surface, so the cross-sectional area of the channel, the speed is going to go up. So as much as you're getting benefit from increasing the surface to volume ratio, you're having an issue here because you're actually speeding it up. Now, first of all, do you understand why the surface volume, the surface area to volume ratio is increased when we reduce the size of the vessel? Do you understand that bit? Okay. So the reason for that is, imagine a sphere, right? Imagine any 3D object. We're trying to look at the surface area to volume ratio. What's the equation for the sphere's surface area? R cubed. For the surface area, it's actually, that's for the volumes. So for the surface area is R squared. So if you divide those two, volume always have a third element in it, third dimension in it to produce the volume, whereas area only has two. That's why if you divide those, we see that reducing the size of objects, it's always that third dimension, which is the volume. When you divide the surface area by volume, it's going to be down there. As you increase dimension, the ratio is going to go down. As you reduce it, it's going to go up. So that's why we use nanoparticles. That's why we try and use micro drug delivery vehicles. That's why we reduce the size of our capillaries, well, we have and nature has. But basically, the idea is that as you make structures smaller, by nature, that ratio is going to actually increase. Now, if that increase of the ratio is at the cost of now speeding it up, it defeats the purpose, right? Because now you get more contact, but then you've got less time, right? So if you do the math, you'll balance that. So the question that I posed there was, does this happen in reality? That the overall cross-section, if you cut the capillary levels from the middle, the overall cross-section of all of those is going to be greater than the arteries and arterioles, right? The question is that. To answer that question, and we already know the answer is yes, the cross-section is greater and the speed isn't going to be sacrificed, meaning that we won't speed it up. But I'm going to take you through a voyage. Let's start from here. So again, I mentioned that all our natural structures have the same growth pattern. This is actually what we call slime mold, type of mold, and it goes really fast, so greater than that for 12 hours to large concentric square area. And people use this to study a lot of the different phenomena that happen even in our vascular system. Right? They want to look at the response of vessels to stimuli. They design a microchip, they have the stimulus there, and they let these grow inside it. And it basically accelerates or speeds up the study because the same growth structure. But anyway, the reason also that we're studying these structures is that you may want to mimic the organ geometry in a tissue that you're printing or producing in the lab. And this has become more and more important. People have been now starting to look, from those simple basic structures that are looking more like an engineered lattice. Now they're moving towards natural structures, and doing this, they actually look at the patterns that happen in our bodies. They look at the source drain system that happens as the hormones and the growth factors are distributed within the tissue. So they actually have computational models that generate these based on the same algorithms that happen in our body. And so that's why they get these natural structures. And that one, similarly, is based on the same growth patterns that follow Murray's law. Now, so it's very important not just for today's topic, which is understanding the cardiovascular system, but also to design any sort of fabricated tissue. You need to have a network to support the growth, and this is going to be a crucial element. So let's now zoom in to one of those junctions. Okay, what I'm trying to arrive at is a comparison between the cross-sectional area at the capillary site, or after the branch, after that splitting, and the one before. Right? I want to see whether the cross-sectional area is increased as I travel through the junctions to get to the capillaries. How am I going to get there? The first thing I have to do is somehow figure out, if I've got a D1 diameter coming in the junction, what are my diameters going to look at when I exit the junction? So I need to do some proper calculation and modeling. What do we know about this junction? What's the first equation that you can get? Yeah. Yes, exactly. So the flow in, if I call this as a Q1, is going to be equal to Q2 plus Q3. Perfect. So that's at least a conservation of mass. We've got it there, right? So the flow rate at the inlet should be the same as the sum of the two outlets. Now I'm going to refer back to something else that we know, which is the resistance of a channel of a certain diameter and radius r. If I write that again, you know what this equation is, in the form of V equals IR, or delta P equals Q times that resistance, or the inverse of it is both similar. Okay? You'll see that resistance there, and how resistance is tying flow rate and pressure, just like you've seen before. Now here is where we're going to get a little bit more involved. Power in a system, in a mechanical system, like if you're pushing the box, right, you've got a velocity times the force that you're putting on it, right? Or in other words, it's the force times the distance you travel, which is energy, over the unit of time, which is the amount of time you spent delivering that energy, is also power. So it's basically force times displacement over time. Now, if I had, instead of a box, a piston inside a cylinder, like a syringe, that's got fluid in it, right? What am I trying to do? I'm pushing the piston, trying to overcome a pressure inside that, and that pressure is basically hydrostatically exerted on the entire surface of that piston. So I have to multiply by that surface to get the overall force required to push that plunger, to push that piston. So I've got, I'm rewriting that in terms of the pressure that I have to overcome. Okay, now this is the same if we're looking at a package of blood that's pushing the package ahead of it through the circulation. It still has to do the same, it's just like a piston plunger. There's a pushing it through the cylinder, and it has to overcome a pressure and multiply that by the area of that cross section, which is what we're actually interested in. That's the same formula. Now I can take the area and the distance, put them together, all that gives me the volume of the cylinder, volume of that vessel. So I've got the pressure difference times the volume, and I've got time here. Now what is volume divided by time? It's the flow rate. So the amount of volume passing through a cross section at a time interval t is the definition of flow rate, volumetric flow rate, a flow through channel. So I've written this in terms of the pressure difference times the flow rate. Very nice. So now if I write it using that formula up there, okay, we're going to have the square of flow rate times the resistance, and that's basically how we can actually figure out what the power consumed by the heart, actually. This is the power your heart is putting in to actually maintain the flow. Now, there's another element too. And that other element, apart from viscous drag power, yeah, go ahead. Yes, absolutely. So we started from the definition of power. So if I've got, it doesn't matter whether it's what's full of stuff, if it's a liquid package here. Oh, yes, yes. So this is basically using that derivation that we just had, which is pressure difference times flow. And then flow here, flow rate, is equal to, so I've just put that in basically, I put the pressure difference, substituted that here, so it's now Q squared times the resistance. Yeah. So those two formulas are actually what got us to this. Now, apart from this, which is the fluidic power needed to get stuff through, get the flow through, we have another element, and that is the power consumed to maintain the blood. Now, this is a very, it's difficult to really clearly explain it, but look at it from this aspect. So we have metabolic rate, right? The metabolism, the molecules in the blood cells, all of that requires an energy, right? And there's a constant change of the forms of energy as blood travels through. You've got heat generation, you've got chemical reactions going on in the blood, you've got dissipation of the heat, you've got the kinetic change of the kinetic energy that drops as it comes. You've got all sorts of energy transformation, which is really interesting and difficult to fully encapsulate in this image. But what we do to simplify is we know that it's proportional to the amount of material in the veins or the arteries or whatever vessel you have, because it is required to maintain the physiological stuff happening in that, right? The enzyme degradation, maintaining the temperature of the blood, all of that. So this is another source of power that's the physiological power, we call it the metabolic power, and that's always going to be proportional to the volume or the mass, but because we know the density, those are interchangeable, of the blood. So this critical element, which comes from metabolism, is going to be a constant K times the volume. Some constant K that you can look up from tables. They've done measurements based on various metabolic events, and you can actually extract that. So the overall power is going to be the sum of the fluidic power and the metabolic power. Now, the last piece of this, what's the last piece? The last piece is to minimize that power. That's what evolution has done for us. And we are now going to do it with a derivative, right? So if you equal the derivative of a function to 0, that's going to give you the E. And so to figure out where the minimum or the maximum of that is, we're going to actually take the derivative, and derivative with respect to radius, because the radius is the variable here. That's what we're trying to optimize for, right? So we've got, for instance, we're looking at this plot. On the y-axis, you're going to have power. On the x-axis, radius. And we're trying to find, looking at this plot, what point is the power performance the best if we had the capacity to change the radius. So doing that, taking the derivative, bring that equal to 0, you can now shuffle terms around, but first just take the derivative, and you already know the derivative of r to -4 is going to be -5 times r to -5. So I've eliminated the constant. We don't really care about that. I've kept the main terms here. Okay, viscosity is constant. It depends on the blood. Viscosity is constant. I've eliminated length because that's irrelevant. We're not changing length again. It's a fixed length. We're just basically basically modulating radius. And I've kept the q squared, I've again eliminated pi there, and I've kept the derivative of that first term as the r to the fifth power. And then for the second term, that's going to be r, okay, because if we take the derivative of r squared, it's going to be 2 times r, and all of the others are constant. So to simplify that, if you take the derivative and leave the variable terms, you're going to see this equation here. And what this is telling you is that Q, the flow rate, is proportional to RQ. If the flow rate, this is really important, this is what Murray realized many years ago, is that if the flow rate within your circulation is proportional to the cube of the radius, not the square, cube, it is going to have an optimal power consumption as it travels through. And people studied this in Leeds, everywhere else, and they saw that, yeah, this is actually true. This is exactly how they've been designed. Now, if we again look at the context of that junction, what that tells us is that the cube of the, at least if we want to optimize power, the cube of the incoming mother branch should be equal to the sum of the cubes of the two daughter branches as it actually exits the junction. So that is critical. Now that can answer your question. Is the overall cross-sectional area after the branch on the capillary side greater, or is it actually the initial area? Who knows what we've got to do after this? What should we do now? We've got to compare those. We've got to compare the cross-sectional area at the outlet and the inlet. How do we do that? Well, the cross-sectional in the inlet is the square of the inlet diameter. The outlet is the square of the outlet diameter. Very simple, right? So the cross-sectional area, the area of a circle. So I've got that, and I've added basically what we just found. And this is the comparison we need to conclude on this topic, and that is the square of the diameter, comparing the square of the two outlet branches or outlet vessels with the square of the inlet one. Now, which one's greater? Outlet, yep. But to do that mathematically, I expanded these, put them to the power of 1.5. This side is going to be the cube now, this side is going to be the expansion. That's a very difficult expansion to calculate, but what you know is at least it's got these two terms, plus a bunch of others. So this side is indeed greater than that, because these terms cannot be. So what we've realized here is that indeed, when it gets to the category levels, the area, the cross-sectional area is going to increase overall. And what that means is that, yes, if you look at the velocity of blood flow as it goes from the aorta all the way to the vena cava, it's going to actually drop significantly in capillary level, slowing down, getting to that laminar cycle, but also allowing enough time to exchange at this capillary level just before it's pumped back through the tank. So that's the third point that you want to know. And the reason you want to know all these points is when you're designing a stent, when you're looking at the diffusion of drugs through the walls of a drug-eluting stent, you want to know what type of flow do I have in this region. You want to know what the flow rate, what the pressure is. If you become part of a company like Biomedical, like Edmunds Scientific, as an engineer, you don't need to know all the jargon of FEM simulation. But if they're designing a product and you're in that executive meeting, you want to be able to do a back of the envelope calculation and see if that idea even makes sense or not. Is that pressure looking right? You have to have these engineering quick access formula in your mind, similar to the resistance of a tube, which is very simple, but gives you an intuition when you're designing any sort of system. And that's why, although I didn't want to extend this to 5 other concepts, but these 3 are the critical ones you want to know. You want to know how to derive these different flow characteristics, meaning pressure and flow rate. And this gets even more exciting when you add heat transfer. Heat transfer from the blood to the tissue also influences this. You've got interstitial flow, you've got diffusion of the substances. It's very complex to model the entire cardiovascular system, but this actually gives you a rough approximate 80%, 90% close to the final result, actually, which is good enough. And a lot of these companies actually just use these. So with that, I'm going to conclude, and just what we're going to have coming up is a lecture or 2 on cardiovascular disease. Then we're going to look at biomedical devices, implants, and innovations in this area to tackle those various diseases. And then we're going to look at the materials used in those, the various technologies used in those, different types of heart valves and stents, and you're going to get more and more intrigued by the sophistication of these systems. And then, yes, we'll have the synchronous lecture next week talking about this stuff, and following that, the 7th week we're not having anything. Then the 8th week we're going to have lectures and labs, and continue on from there. So just going to ask if you have any questions. Anyone online has any questions? Yes. Yeah. Yes, absolutely. So if you take the derivative of this function here with respect to r, what are these? The 8, the pi, the viscosity, these are all constants, right? Even the length, because we're not really optimizing the length. So I can minimize all of those in a constant k, right? And similarly here, there's a constant times pi times L. It's basically r squared times the constant, and here it's r to the 4th power times the constant. Now if I take the derivative of that, all those constants, so definitely you can collapse them to one constant, right? Because you can, if you put that equal to 0, you can take one term to the right-hand side, and then collapse those 2 constants to one constant, multiplied by the radius, which is the derivative of the second term, because it was r squared, now it's going to be r. And in the first term you have now, we had r to the negative 4th power, now you have r to the negative 5th if you take the derivative. And then you've got q squared, which is important, it's our main function, so we want to keep it there. So if now you switch the term, mainly you can see that now q squared is equal to cr to the 6th power, q is proportional to the square root of that, which is r to the 3rd power.
So what is the CTE?
Oh, it's constant, sorry, that CTE means it's a constant.
Oh.
Yeah. So some write it as constant, the CTE, but what it means is C is a constant there that basically shows all the various constants involved in here. So you can basically write that as an expansion based on pi, L, the viscosity, and then you can find what that constant is.
So if you were to do a calculation, would it be useful at the beginning of the calculation to just find what C equals to? And if you want to actually find like an actual value, then just at the beginning of the calculation, find what C equals to then just be able to substitute it at the end.
Actually, what you can do is you can again find the description for C based on those variables and calculate that, and then use it here. But the thing is that as we travel through the circulation network, we care less about this because this is influenced by many other factors. We care more about the final result we get from that, which is the relative flow rates, the relative diameters. If you want to really understand the proportionality, there are a couple of other factors that play a role too in that constant. Okay. Sure. Any more questions? Let's see if we have any questions online. No, doesn't seem like it. Okay, awesome. We're not going to have quizzes for this or the next week's topics, but in next week's lecture, I'll have a couple of questions for you, which I'll do in the style of that survey thing. Not marked, but just good so you know the content so you can engage in those questions and answers. I hope you've enjoyed the lecture. Jam-packed lots of stuff, but just go over that. The recording is going to be online, and if you have any questions, let me know. Okay? Take care. Hey there, John.
Please upload the slides as well by themselves.
Absolutely, yes, yes.
Thank you very much.
No worries, no worries. Thank you.